All right, today we're going to pull back the curtain on something that's absolutely fundamental to modern AI. How in the world does a machine actually learn to read our language? This isn't just a small detail, it's the very first critical step that lets an AI understand what you're asking, write an email, or even generate code. We're diving deep into something called byte pair encoding, or BPE for short.
When you type a question into something like ChatGPT, it really does feel like magic, doesn't it? But way before any of that thinking happens, the AI has to do a crucial first step. It has to actually read what you wrote. And that's really where our whole story begins.
So this first step, it's called tokenization. It's really just the process of chopping up a sentence into smaller, meaningful chunks that we call tokens. You can think of these as the basic building blocks, the vocabulary that the AI is going to work with. But the big question is, how does it decide where to make those cuts?
And that, my friends, is where byte pair encoding comes into the picture. BPE is this incredibly clever and super popular algorithm for doing just that. Fun fact, it was actually invented for data compression, for making files smaller, but AI researchers had this light bulb moment and realized it was the perfect tool for teaching a machine to build its very own language from the ground up.
The best way to get your head around it is to imagine you're building a custom dictionary for a specific book. That's pretty much what BPE does. It starts with nothing more than the letters of the alphabet, and then, step by step, it learns which combinations of letters show up most often and turns them into new words for its dictionary.
Okay, so what's the actual recipe here? How does it all work? Let's just walk right through it. You'll see it's surprisingly simple and, honestly, kinda elegant. The whole process is really just a simple four-step loop. First, you start with a vocabulary that's just all the individual characters you have in your text. Easy enough. Then, you scan through and find the pair of characters, or tokens, that appears most frequently, side by side. Next, you smush that pair together into a single brand new token and add it to your vocabulary. And finally, you just repeat that over and over and over again, building longer and more complex tokens until your dictionary is as big as you want it to be. Okay, Siri is great, but let's make this real with a tiny example from Hugging Face's own course. Imagine our entire universe of training data is just these 5 words with these frequencies. This little collection is what we call our corpus.
So first things first, we shatter every word into its most basic parts, the individual characters. Our starting dictionary is literally just the letters B, G, H, N, P, S, and U. Now the game begins. We need to find the most common pair.
So how do we find the most common pair? Well, we just count them up. The pair U and G shows up 10 times in hug, another 5 times in pug, and a final 5 times in hugs. Add it all up, and that's 20 occurrences, which makes it our winner. It's the most frequent pair in our little world. Okay, so we perform our first merge. The pair, UG, becomes the new token, UG. We add UG to our dictionary, and then we update our corpus. See how the words hug and pug on screen are now represented a bit differently?
And we just do it again. It's a loop, right? So we scan our newly updated text and hunt for the next most frequent pair. This time around, it's oo followed by n. It appears 12 times in pun and 4 times in bun, giving us a grand total of 16.
And there we go, our second merge is complete. The token un is officially born, and we add it to our dictionary. You can see our vocabulary is getting a little bit richer, and our words are being compressed into these more meaningful chunks. Let's do just one more. Now, the pair HUG is the most common one we've got. It shows up 15 times across both hug and hugs. And notice what's happening here. This is cool. We're now merging a single character with one of the new tokens we just created. And right there, that's the magic of BPE. With this merge, the entire word hug has become its own single token. The algorithm has effectively learned that hug is a common and meaningful unit in our text. We just keep this going until our dictionary hits whatever size we're aiming for.
All right, so we've trained our little mini dictionary. Now what? Well, let's see how it actually performs when it gets a new word, one it's never ever seen before. This is where the rubber really meets the road.
Let's look at this great side-by-side comparison. If we give our model the word bug, it handles it like a champ. It recognizes B from our original alphabet, and it recognizes our newly learned token, UG. Perfect. But if we give it the word mug, well, we hit a snag. You see, the problem is that the letter M just wasn't in our original training data at all. So the model literally has no clue what it is. It basically throws its hands up and replaces it with a special unknown token, which you'll often see written as UNK. This really highlights a fundamental limit. The model can only understand what it has been trained on. And that's why the quality and the sheer size of that training data is absolutely everything.
Now, that might sound like a pretty big flaw, right? But here's the thing. BPE is used in pretty much every single major language model out there. So what gives? Why is this simple, kind of imperfect method so ridiculously effective? Well, the answer is tucked away in some really fascinating and recent computer science research.
For the longest time, even the experts were kind of shrugging their shoulders. As this recent paper puts it, the reasons for its good performance are not well understood. It just worked. It was a classic case of brilliant engineering just getting way ahead of our deep theoretical understanding.
Well, it turns out that finding the single mathematically perfect set of tokens for a piece of text is what computer scientists call an APX complete problem. Look, to put it simply, that just means it's so mind-bogglingly difficult that we don't think any computer, no matter how powerful, could solve it efficiently. It's practically impossible. But here's the beautiful part. BPE doesn't even try to find that perfect, impossible answer. Instead, it takes what's called a greedy approach. It just finds the best next merge at each step without worrying about the big picture. And it turns out this simple, maybe even naive shortcut is a remarkably good one.
And this is the kicker, the big reveal from that paper. They proved, mathematically, that even in the absolute worst case scenario, the BPE algorithm is guaranteed to find a solution that is at least 62.5% as good as that mythical, perfect solution we can never find. It's a proven, high-quality shortcut. That's a pretty good grade on an impossible test.
All right, so let's tie this all together. BPE is a simple, looping algorithm that lets an AI build its own vocabulary from scratch just by merging the most common pairs. It organically creates these meaningful subwords that can handle common words and rare ones pretty well. And while it's not perfect, we now know it's a proven and theoretically solid shortcut that happens to be the very first step in how AI learns to read our world.
And that just leaves us with this one kind of mind-bending thought. BPE is a brilliant, practical hack that gets us surprisingly close to an ideal solution. But it just begs the question, if this is the clever shortcut, what would a perfect solution even look like? What other breakthroughs in understanding language are still out there, just waiting for us to discover?